All right, well, since it's 12:05, I know we'll probably get a couple people show up still from here, but I think I'll probably get started. So thank you all for coming. My name's Phil Harris. I'm the president of Insight Analytical. And, we're Calgary, Canada-based provider of analytical solutions for measurement issues. And we like to try to run a regular webinar series in order to kind of help us to bring some information out to our clients about ways certain measurements can be done. And of course, we tend to focus somewhat on the products that we're able to provide and how we might implement those solutions in the field. And so today I'm going to talk a bit about online analysis of rich natural gas streams. And so specifically, I want to talk about some of the streams that that can be more difficult to analyze because they're perhaps right near their dew point. Perhaps they have a high variability in composition. So moving a bit away from, say, sales quality natural gas, and instead looking at rich gas streams, and especially looking at applications where we want to analyze these products to try to provide some feed-forward control for a combustion type process. So, we're going to be talking about combustion feed gases primarily. And so like I said, we're going to talk about rich feed gases and burner controls. I'm going to start off talking a little bit about who Insight Analytical is, talk a little bit about what I mean about when I talk about rich versus, say, lean gases, talk a little bit about why we want to do burner controls, why it's important that we make some measurement of these gases in order to optimize how our burners are operating, and then talk a bit about some technical solutions which can be used for these types of applications. I'm going to mention a couple of other technologies, but specifically, we wanted to do this webinar because we have a couple of customers who are asking about certain applications where the JP3 near-infrared spectroscopy appears to be the solution of choice for them. And so I want to talk a bit about JP3's near-infrared spectroscopy and how we apply that to some of these rich gas streams and what kind of data we see. As I usually tell people in these, I'm very comfortable with being interrupted. 3 kids, get used to it all the time, get used to being told you're wrong. So if anybody has any comments or questions along the way, please feel free to just jump right in. You can either put them in the chat, which I'll try to keep an eye on, or just feel free to turn on your mic and interrupt me and ask. So with that, I'm going to talk a little bit about who Insight is. We're a Calgary-based systems integrator, distributor, and manufacturer of some sampling system products. We run a Northeast Calgary in Alberta, Canada, 20,000 square feet accessible shop, 9 bay doors, 10-ton overhead crane that lets us bring a full analyzer building or panel in straight off the back of a flatbed. So we've got good access for doing systems integration type work. For the Canadians here, Canada has a specific set of regulations around pressure equipment and pressure vessels and pressure containing devices. So we're an AB83 compliant fabricator, which means we can basically put a CRN number, a Canadian registration number, on the products that we build. And we manufacture, we've shipped CRN products to Alberta, BC, Ontario, Saskatchewan. A lot of the folks that are here are people I've worked with for a lot of years in different companies. And so we brought together some people with some great skill sets. We have fantastic documentation capabilities, drafting and design resources. So able to fully meet all the requirements that typically come up from the large engineering companies, the Fluors and the Bechtels and the like when we do projects. Journeyman electricians, journeyman instrumentation techs, qualified team to not only build systems, but to install them out in the field. And we'll do full factory acceptance tests right here in Calgary. I will also mention you will get a follow-up email from this, which will have a copy of all the slides, as well as some other technical information about some of the applications. Oops, just having to keep an eye on people as there still have people joining. From the systems integration side, we will do full systems integration, everything from small sample panels right through to full analyzer buildings. So we'll do custom sample systems. We'll do the process analyzer integration work with that. We'll do PLCs and automation right through to full analyzer buildings. I tend to like showing this picture that I have in the background right now because, we have in here, obviously a full analyzer building. These are two of the composite samplers we have built, light liquids composite samplers. Sorry, admitting a couple of folks. There's a solvent flush tank sitting back here. This is a system for natural gas condensate. It can be fairly waxy. And so one of the things we wanted to do to make sure it was low maintenance was give the ability to back flush the optical cell. There's a JP3 near infrared sitting over here just off camera. There's 4 floating piston cylinders in there that are being controlled by the PLC, and the PLC can actuate when samples are getting taken and grab samples being taken, automate that process, correlate it with the spectral data that's going on from the analyzer. So there's a lot going on in this building, and it's one of my favorite ones to show. We will run projects right through from front-end engineering design. So to try to help you to evaluate what's the best technology for me to put in an application, through detailed engineering design, through fabrication, through field install and commissioning. And one of the things we really focus on is having a strong service team that we can support our customers out in the field. So I want to talk a bit about lean versus rich natural gas. When we look at kind of the processing that goes on, right? If we go right from producing wells, gathering lines into some kind of gas processing plant, so there'll be compressor stations along the way, there's a change in the gas quality that's happening all the way through here. The closer we get to the wellheads, typically, the gas is richer because the heavier hydrocarbons haven't been taken out of it. And it's also a lot more variable. By the time we get into this transmission part, when we're getting close to city gates or big volume customers, it's after the gas plant, after straddle plants, after a lot of the liquids and the variability is taken out. And often that gas is sitting and running around, 980 to 1,050 sort of BTU, depending on systems we're on. But upstream of there can be a lot more variability. So I kind of tried to show what the difference is between, say, lean, rich, and what some people might refer to as wet gases. Lean natural gas, the stuff that we'll see in pipelines, is often in that, maybe 85 to 95% methane range. It's usually running around 1,000 BTU, and there's not a lot of variability, and there's not very much for heavy hydrocarbons there. As we get closer, perhaps, to inlets to plants, what we refer to as rich gases, we may be getting up more into that 1,500 BTU range, and having higher ethane and propane concentrations. On other places, if we're looking at casing gases from associated gases for producing oil wells and things like that. We can get to these very wet gases that have high levels of propane, butanes, and pentanes in them, and BTU numbers running all the way up into the 2,000 and 3,000s. And so, these are quite different fuels. They have a lot different oxygen demand for how much air is needed in order to burn them. And so if we're trying to run burners on, say, a variable fuel, which might be a blend of some of the lean gas we're buying from a natural gas producer or pipeline, and some perhaps gas we're producing at site, rich natural gas, casing gases, wellhead gases, these can have a lot of variability, and it makes it more difficult to control burners. And that's where things like feed-forward control analyzers to do full burner control become important. When we think about, what goes on in a burner, it's pretty simple, right? Whether it's a natural gas turbine or a reciprocating engine, what we do is we mix fuel and air, and then we ignite it. But what we have to realize is that different fuels, different fuel compositions have different demands or requirements for air. And so what we become concerned about is how interchangeable our fuels are going to be for the type of engine that we're running, and what the effect of that fuel variability is going to be. In things like gas turbines, we can actually damage the turbine by running too rich a fuel to it. And so it's important, you'll see, and we have Jochen on here from Amatec, the hydrocarbon dew point analyzer, that a lot of people who are putting in large compressors would put a dew point analyzer up there in front of it to try to ensure that they don't get too much rich a fuel into that engine because of the potential problems it can cause. Flame outs, damage to the turbines. Same with big reciprocating engines. So we've got to have an understanding of what's my fuel composition like. If you think about it, this is why we have specifications on gasoline quality and octane numbers, or diesel and cetane numbers. We want to know what the combustion properties of that fuel is, so that we can tune how we're going to mix our air to fuel ratios to get the best efficiencies out of our engines. When the fuel starts to have a lot of variability, when we can go from saying a methane-ethane stream to a methane-nitrogen stream, well, they have quite different air demands. They have quite different oxygen demands. And so as a result, we need to know if the fuel is changing and then make adjustments to our air to fuel ratios. So why do we want to measure these things then? Because if we can adjust our air to fuel air ratios, we can reduce pollution and emissions, and we can get better performance out of the engine. We can tune its performance better, and we can get better mechanical protection for the engine so that we don't run it dramatically off ratio and have mechanical issues, damage to the engines. Literally, you'll see these big reciprocating engines, they can get too rich of fuel in them, you can damage and blow up the engine essentially. So there's a lot of issues associated with not having that correct balance between how much air and how much fuel. From an efficiency perspective, if we put too much air in, we waste a lot of heat. We have to heat that air up. So we actually lose efficiency from the engine. Also, if we put too much air in, we find that our NOx emissions will increase. And so we have environmental associated issues. If we don't put enough air in, if we have too much fuel and not enough air, some of the fuel doesn't get burnt. And so now we've just wasted that fuel. We can get issues like what we refer to as flashback and flameouts, where because there's more fuel there than there is air, the flame propagation doesn't occur properly. And as a result, we can actually get damage done to the engine or hazards related to possible explosion risks. As well, if we run too high a fuel and not enough air, some of it doesn't get burnt. So again, we increase our VOC emissions, volatile organic carbons. So optimizing this air to fuel ratio is important because it saves us money, it improves efficiency, and it reduces emissions. And especially on these large engines, things like turbines and compressors, we want to make sure we're protecting our assets. Damage to say a turbine that's part of a gas compression system or being used at a wellhead for fracking fluids, it leads to downtime, and downtime costs us a lot of money. So we want to look at how we can measure, and there's a bunch of different ways we can go about trying to measure fuel quality. One of them, and the one that we commonly think of on, say, natural gas transmission pipelines, is gas chromatography. We separate components in a flowing column. We allow carrier gas to flow through a column or multiple columns. And it's been a very well-established technique. It's got good precision. It gives us a full stream composition. It works really well on, sorry, I want somebody to let in here. I don't multitask well. If I have to click someplace, I have to stop talking. It works great on really dry gases. Gases that don't have any particulate in them, that don't have any, say, bitumen-like products or tarry-like substances can work fine. Problem is they're easy to contaminate. As you can see up here, lots of small tubing, 1/8-inch tubing. We have to do a lot of sample conditioning. And also they are slow. A typical chromatograph will take several minutes. A typical chromatograph will take several minutes in order to do analysis. So it's not suitable for a process control application, not for something where we're looking like a burner that, we can have very fast changes in fuel compositions. Another alternative, and one that is more suitable for process control, is to use what's called the residual oxygen measurement. You basically take a small sample of the fuel, mix it with air, run it through a combustion furnace, and figure out, well, how much air does it take to burn this fuel? I can calculate then what's either referred to as my CARI, combustion air requirement index, or my WABI index, which is a measure of really what my air to fuel ratios need to be. Has good precision, can handle a wider measuring range, typically than something like a GC might, and it's fast. It's built for process control. But again, we often have to concern ourselves because it has a small injection valve, just like a GC injection valve. We have to concern ourselves a lot with, well, is this going to be a good sample to bring to the analyzer? What do I need to do in the sample conditioning system to protect?
Oh, yeah, so I was wondering if I could get an appointment with Wendy tomorrow. Okay.
Your mic is mute. Your mic is mute.
Sorry, I meant to mute someone else's. Thank you.
Good. No problem.
Yeah. So the residual oxygen method is, it's a reliable method for use in some applications. Again, where people sometimes had trouble with this, is when there's a lot of heavy tar-like substances, naphthalines and things like that, because of how they impact the injection valve. And again, we're going to start talking about applications like putting these air to fuel ratio analyzers on things like mobile compressor skids. that are being used for fracking wells. And so, you know, we're going to have another set of requirements. They're going to want devices that we can start up quickly, that transport well. And so, you know, like I said, we're going to look at a couple of other technologies yet. Another method that gets used, and you know, we've seen come up in the flare gas side of things, especially in the U.S. with EPA requirements, is mass spectrometry. So things like the X-Trail mass specs. They'll give us a full stream analysis. They'll give us a sulfurs analysis as well. They're fast. They're multi-stream capable, so they can be used for process control in these applications. But again, small inlets, so streams that are going to be physically difficult to condition to make suitable for the analyzer can be especially problematic for some of these types of devices. The other thing is that for many of these devices, whether it's the Wobbe index analyzers or the mass spectrometers, it requires that the pressure has been let down for the gas. And, you know, that doesn't sound like a big deal. We all put regulators in. But because of effects like Joule-Thomson cooling, we can sometimes introduce compositional changes that happen when we try to change the physical state of the fluid, lower its pressure, etc. So it can be beneficial to have a technique that's able to measure at line conditions.
Spectroscopy.
And so one of the things that, you know, one of the things I'm going to focus on today is the use of near-infrared spectroscopy to do these kinds of measurements. We can do a complete hydrocarbon stream composition and BTU analysis in real time, fast, built for process control, handle very wide measurement ranges, big changes in compositions. We can actually go, the unique thing is with model switching, we can actually go from completely different gas compositions and do the same, just have two models that do the analysis of these different streams. Multi-stream capable, fast, like I said, built for process control, and very mechanically robust and transportable. So if we're going to put this on something like a mobile compression skid for fracking wells, well, oftentimes, you know, when these guys go out to frack a well, there's not great highways out there. Go down back roads, you want a device that's going to be mechanically robust and can be moved. And when you get it at site, it has to start up fast and be up and running. And so some of the important things that we're able to achieve with this technology is to be able to handle that widely variable stream composition, to measure at line pressures and temperatures, not introduce any phase changes, and get that measurement up and running immediately when it gets on site. So a couple of applications that we've that kind of spurred this talk was, we have some clients who are looking at oil sands burner feeds. And so, you know, in Canada, we produce the oil sands in Northern Alberta. We produce bitumen, and with that will come associated gas. That gas that comes back has been in contact with steam, has been in contact with bitumen, and it can have a lot of small particulate that is sticky. It's bitumen-like, it's like tar. And so it creates havoc for a lot of analyzer sample systems. And we produce this bitumen by making steam. So we run big boilers, steam generators, to make steam to help produce the bitumen. And so we'd like to have feed forward control on those burners. Now, we could get that by just using sales quality natural gas all the time, but then we have to buy that sales quality natural gas off the transportation grid. We have this associated gas that comes back. It has high liquid dew points. It's hydrocarbon rich. It's got highly variable compositions. It's got lots of sulfur compounds in it, and this can cause problems for burners as well, but also for analyzers. because of sulfur deposition. And so we needed a technology that is capable of dealing with these rich, wet, dirty gases, essentially. And it's one of the places where some of the unique features of how JP3 does this measurement is actually got a lot of benefits. The other thing we're seeing is that for well fractionation, or for fracking wells, when we're looking at the compression systems that are put in, we frack wells by basically pumping a high pressure mixture of water, sand, and some fracking fluids into there to help crack the rock underground. And so we have to move a big compressor onto site. We can run that compressor on diesel. But when you've got a big frac spread out there, that's a lot of diesel trucks showing up on a regular basis and has a lot of cost. If we can actually take the produced gas that's coming from some of the wellheads that have already been drilled, the raw gas. So, again, we talked early on that there's this idea that we have produced gas that comes from a well, and they can have widely variable compositions. Normally, we send that off to a gas plant to get, if you like, refined, purified. What we'd like to be able to do is run these burners on the gas that's available at site. So if we can get that gas directly from the well pads and run these burners, it allows us to use a less expensive product that has less environmental emissions than running on diesel does, and doesn't require all these diesel trucks bringing in fresh fuel all the time. The fuel is available at site. Now, again, these are transportable rigs. So this is where this need for fast startup and shutdowns and the availability to get online and running very quickly is important. So the solution that has been implemented is based on near infrared spectroscopy. JP3 Measurements Company out of Austin, Texas. They have a rather unique infrared spectrometer, and that's a broadly tuned, a wide wavelength range it can cover laser device, sectionally stable, very bright, very high signal to noise ratios. The beauties of it is no moving parts. So again, we said we wanted something that was going to be transportable. It's nice when something is mechanically robust. We're worried about things like plugging. Well, this is built with big 1/2-inch tubing and piping, not little 1/8-inch pieces of tubing. So mechanically strong, doesn't get plugged very easily. Multi-stream capable, can handle more than one measurement point. Fast, near real-time analysis, often under 15 seconds. Future software upgrades are coming out. It's going to get that even faster. There are virtually no maintenance devices. There's very few user serviceable parts in it. The one thing that does require any maintenance, possible maintenance, is cleaning the cell windows, which is about a 1/2 hour task. So it can be maintained very easily. It provides full data services out to the cloud. So you can log in remotely and see how analyzers are running and do remote diagnostics. From Insight's perspective, we sell this product in Canada, and we run field support for this out of Grand Prairie, Edmonton, and Calgary. I'm going to talk a little bit about how it works. When we think of, when I originally was trying to sell these things and tell people, well, we're going to do a measurement in your crude oil by shooting a beam of light through it, where they say, well, that's ridiculous. You can't get light through my crude, it's jet black. Well, that's because things like crude oil absorb all of the light in the visible region of the spectrum. That's why they're so dark. However, as we move outside the visible region and beyond the red into the near infrared, what happens is hydrocarbons start to absorb less and less light until we get out to around 1600 nanometers. And when we get there, there's this bunch of absorption bands. And the shape of those absorption bands allows us to quantify to identify which hydrocarbons are there. And the magnitude of those absorption bands, how big they are, lets us determine what the quantity of the hydrocarbons is. So we can use near-infrared spectroscopy to do a real-time analysis of what hydrocarbons are there and what concentrations are there. Again, we need this to be mechanically robust. And so one of the things that we use is what we refer to as a flow cell. This is basically it's a big block of 316 stainless steel. Inside of it are two synthetic sapphire rods. Sapphire has the properties that is the second hardest material next to diamond. And so as a result, things like sand, clay, bitumens won't damage the optical surfaces. It's also very good at transmitting infrared light. And so we can use these to provide a vehicle that the beam of infrared light can pass through the process fluid. So what we do is we mount the analyzer someplace remotely. And from the laser source that's in the analyzer, oh, my pen just stopped writing. Sorry, technical difficulties here. Oh, pen stopped working. Where did it? One moment here. Let's try this again. Okay. All right, we might be penless for a bit. We can shoot remotely from this laser through a piece of infrared, through a piece of fiber, connect it to that flow cell, and allow the laser light to pass through the fluid that's moving in the cell. This then allows, allows us to interrogate what that fluid is, use the pattern of infrared absorption that's occurred, pick that up on another fiber and send it back to the detector. And that allows us then to do the analysis of what species are present. So these can make for very simple installations and flow paths. We can mount that flow cell in Canada, because it's cold, we mount it usually inside of a heated box, and we put it right near the process connection as close as we can go. In the US, they'll often just put these outside. It allows us to do that measurement very close to the operating unit, which helps us to get really good response times. We have short flow paths to get through. So we can look at the entire process by which this operates, something like this. We can take the analyzer itself, mount it someplace remotely. That's this box down here. It can go into an MCC building, a control room. No hydrocarbon fluids are going to come to it. It sends a beam of infrared light out that passes through that flow cell and is brought back over fiber optics. From someplace in the process that we want to measure, we've had a sample tap and a return point that are at differential pressures. That gives us continuous flow through that flow cell. So now we've got the laser beam shooting across this flowing fluid. We measure the infrared spectrum, run it through our data analysis algorithms, and can come out and do a full stream composition. We can do this for gases or for liquids. All the fluid is being returned to the process. So, one of the concerns a lot of people have right now are things like methane emissions. How much I've been in the analyzer business for coming up close to 40 years. And it's only recently I've had people start to ask me, well, how much does the analyzer flow? How much is it going to vent? Because people are worried about methane emissions from a greenhouse gas perspective. So one of the beauties of this technology is we can sample and return right to the same process. We're doing this at the flowing conditions of the process line. Sample line, same temperatures and pressures. So we can mount this right out at the frac compressor. So we can put it right onto the part of the compression skid, take a sample off that natural gas line or that fuel line and run it through the spectrometer, get real-time composition, real-time BTU. This allows us to put feed-forward control to the burner, lets us adjust air-to-fuel ratios. We're running at process pressures and temperatures, so we don't have any phase changes. We don't have any places that liquids are going to drop out when we take a pressure drop. We can get these things started up and quickly after arrival on site, and it's mechanically robust and transportable. Let's see if this works. Now, this is supposed to be animated up there, but why isn't the animation? Let me see if I can. Yeah, we have to come back to it. Too bad. That's a little video movie that just showed. The movie sort of shows and runs through and shows you how we start out on a very other. Going? Okay. Anyways, these are changes in methane concentrations and ethane and butane concentrations happening in real time. For some reason, the animation doesn't want to play on this laptop. I've got another graph that shows that sort of thing. So when we talk about fuel BTU variability, there can be big changes that happen over short periods of time. So we've got this this frac truck sitting there, and here we show the JP3 analyzer sitting right there on the skid, and in real time, we can be measuring the BTU quality of the gas. And you can see they were running around, 1080 BTU. And they had an event occur where they went very rich. BTU goes all the way up to 1350 over the space of several hours. So if they had no way of monitoring that, they would be running at completely the wrong air to fuel ratios and be running extremely rich on the fuel side, causing them a lot of problems. So having the analyzer there, we're able to actually see these kind of excursions that can happen and adjust air to fuel ratios. I know these are a lot of graphs that are impossible to see, but I'm going to zoom so I can sort of jump in on this. These are sort of some correlation plots that show when we run lab sample and compare them to the analyzer. So we start out at the top there with dry BTU. See a good range of measurement from around 2200 to 3600 BTU there. Here's our methane variations from 0 to about 20%. Our ethane variations from about 4 to about 35%. Propane variations from maybe 10 to 40%. Ibutane from about 6 to 15, N-butane from about 10 to 35. And my point here is that this analyzer in real time is providing us chemical composition of each of these individual components and BTU numbers with no moving parts and no little injection valves. So I'm going to show this going right out to a C6 plus analysis. So if we're out in the field for fuel applications, we may have these dual burner engines, a diesel engine, diesel available to power the engine, natural gas or locally produced natural gas, wellhead gas available. And what we do is we put the analyzer in the middle in there to provide real-time analysis of the fuel. And that lets us then, control that control valve and adjust air to fuel ratios. Kind of not sure what's going on with my PowerPoint today. Okay. Let me get back there. Love having technical difficulties. Okay, there we go. So if we have this online analyzer, we can do this real-time analysis of the BTU and the hydrocarbon composition and provide all the necessary engine protection. For those of you who aren't familiar with this technology, this slide is actually old. There's probably closer to 250 or 300. There's a couple guys from JP3 on here. They might give me more updated numbers. Probably 250 or 300 installations across North America. We got about 50 of them up in Canada now. We're present in nearly all active oil producing regions in continental North America. We've got a good mix of crude, condensate, natural gas liquids, natural gas, refined NGL products, refined fuel products. So we get a large installed base. It's a well-proven technology. In addition to doing things like gas phase fuels for burner control, we put these on crude oil blending skids. So in that building, they're blending butane into crude. Coming through those two black sample lines is sample of crude coming out, flowing through the flow cell and returning back into the process where we give them real-time actionable vapor pressure data. We will put these on condensate stabilizer bottoms. And so this is an installation in Canada as well, where we've got the nice PowerPoint screwing up. Oh, I got a question in the chat maybe. Oh, there we go. From Nate, we have 640 active read points right now. So there's a large installed base for this technology. In this case, we're doing a condensate stabilizer. We've got the analyzer sitting at stabilizer bottoms. The flow cell sitting at the stabilizer bottoms in that heated box, and the JP3 analyzer back at an MCC building where we were able to say, because no process fluid comes in there, we are able to just install that at the MCC and bring fiber optic connections in that connect out to that remote point where the actual process is operating. Some other data from a couple of other applications, we do butane blending into diluted bitumens. So this is lab vapor pressure on the x-axis, measured vapor pressure from the JP3 on the y-axis. You may wonder why I made the dots so big, but it's to try to show that both of those are those dots cover what plus or minus 1 kPa would look like. And so the blue dots were stuff that we had used to actually build the model and the calibration. And the red X's are validation samples that were done. So you can see we cover a reasonably wide range of vapor pressures for this blended butane into bitumen application. On things like deethanizers, again, x-axis is usually lab results, y-axis is the JP3 analyzer results. We're looking at measuring ethane in a deethanizer bottom from between 2 and 8% ethane. Excellent correlation, excellent agreement across a wide range of process conditions. 110 to 170 PSI absolute. This is data ranging over several years. Similarly, results for propane on a DF bottoms as well. So usually the critical control parameter here is ethane to propane ratios. So it allows us to do those, to provide real-time control of DF bottoms. Similar sort of thing on condensate stabilizers. Tried to pack a lot of data onto one graph. So the blue dots are the propane measured in the condi. So down around say 0.2 liquid volume percent. The red dots are the isobutane in kind of the 0.8% kind of range. And the green dots are the N-butane sitting up on the, measured on the other y-axis and sitting around 4%. So again, you know, we can do multiple chemical analysis on the same stream. Again, if you're in Canada, this is all part of meeting a DMC4 requirement for condensate transport. And if we go and we look over here, you know, this is how we did on the DMC4. DMC4 is calculated as 3 times the butane plus the IC4 plus the NC4. And we have, again, this great correlation from being much below the requirement, which is you have to be less than 5%. For a facility, they want to operate as close to 5% as possible. But what this shows is that we have good range to be able to track the variability that there can be in the DMC4 and then provide them that control signal around the 5%. So that wraps me up on most of the technical stuff for this. Give you an idea, just Inside Analytical carries a full line of process analyzers. Of course, we spent a lot of time talking about the JP3 today. Oh, my pen's still not working. We talked about the JP3, but you know, we also carry Z-gas dew point analyzers. I mentioned the XREL as a process mass spectrometer. COSA Xantar for the Wilby index. So 3 of the products we kind of mentioned for this burner control. We can find the right product for the right application. I think that's the most important thing there. So if you do have a process application where you're looking at measuring hydrocarbons or measuring some other process chemicals, I should mention we have a full line of other analyzers as well for oxygen and a number of other things. But with the JP3, we've got multiple applications running now. We're developing more all the time, and the application is really suitable right across the hydrocarbon processing industry, from natural gas and natural gas liquids to crude oil and refined fuels. And at that, I'm going to wrap that up. I'll leave, again, you'll get a copy of the slides, give you my direct number and how you can get a hold of me. And I would be happy to take any questions that people might have. And, or if you have any that come up later, just feel free to shoot me an email.
Phil.
Yes, sir.
Kind of a tough question here, but what is the cost for this kind of a typical installation? What would that be?
Where are you located?
Where?
Yeah.
Well, it could be anywhere in our province.
Oh, okay, okay, but in Alberta here.
In Alberta, yes.
Yeah, yeah. With sample system, so there's a couple of different versions of the analyzer. One of them will only do a single stream, and it's the less expensive version. And there's another one that will allow you to do up to 4 different measurement points. So what I kind of give people as a ballpark number is if you can do a single stream measurement, all in, so sample system, fiber optic runs, installation, all of the samples pulled to build the model, all in, you'll probably end up being around 200,000 Canadian. If you're going to do the multi-streams analyzer, all in, you'll be approaching 300,000 Canadian for the first measurement point and 100,000 Canadian-ish for the additional ones. It depends a bit on how, we use a very custom fiber optic, so it depends a little bit on how far the boxes are away and how long the fiber runs are going to be.
I see. Okay.
That's kind of the ballparks.
Okay. One stream, 200,000.
Yeah.
Okay. Well, thank you.
Yeah. And that's a safe number to work. If you're doing like a budgetary, trying to put budget in, this is what I'm hoping. You want to put budget in for next year for the one you're going to buy, right?
Well, yeah.
Yeah.
Okay, so when you say one stream, You're talking about distillation, right? Because the equipment would be able to do more than one.
Yes,
Am I
yeah.
right?
So
Up
I'm
to
saying
four.
well, it depends. There's two different versions of the box. There's a version of the box that only has one set of fibers that can connect to it. So it'll only do one measurement point.
Mm-hmm.
So we use that a lot of times on things like a crude oil blending skid. And a guy just says, I just want to know what the vapor pressure is after I've done my blend. It's the only measurement I want to make. Then we put the flow cell there.
Okay.
If the guy has a gas plant and he says, I want to make a measurement over at my deethanizer bottoms, and I want to make a measurement of my debutanizer reflux drum, and I want to make a measurement of my condensate stabilizer bottoms, well, then we would put the 4-stream version in and run fibers to 4 different places in the plant.
Okay, and all the measurements will be independent from each other, right?
Exactly. One measurement could be wet inlet gas at the plant, and the other one could be crude oil leaving the plant. Completely different phases, chemical compositions on each measurement point.
Go ahead. Sorry, go ahead.
In fact, in pipeline applications, one of the things that JP3 does is it's a single measurement point, but there's calibration models for different products. So they can be looking at transmix and saying, okay, you're flowing jet fuel down this pipeline. Oh, you just went off spec for jet fuel. Oh, you're now on spec for gasoline. Oh, you just went off spec for gasoline. Now you're on spec for diesel. So as different products are flowing down the pipeline, they can use the analyzer to figure out, well, what product is that? Is it meeting specification? And in that period of time when it's transitioning between two, it tells you how long that blend period is and whether you have to put that to storage for reprocessing.
Okay. So when it comes to communication capabilities, what can it give us? For example, Ethernet.
Yeah, Modbus over TCP/IP is our standard.
Okay.
Yeah. We also have a cellular connection to each analyzer. So we have software that we provide so you can have a remote way of logging into the analyzer, see how it's running. So if you're here in Calgary, but you want to know how the plant in Grand Prairie is running, you can just log into the analyzer and see what the results are.
Okay. What about diagnostic capabilities?
So as a full set of diagnostics, we monitor things like in our flow panels, we usually put in a flow switch, pressure and temperature transmission. So we look at some process variables like, are we actually getting flow to the analyzer? And are the temperatures and the pressures normal for what we would expect for this process? Because one of the problems can be if things get plugged and things like that. The analyzer has internal diagnostics, extensive diagnostics on the spectrometer itself. And then there's a set of, because the data analysis is statistical in nature, we get a measurement of how much error the analyzer thinks it's seeing right now. How good did the data match my models? And it gives a statistical measurement of that. So if we see, for example, an unusual product come through, it'll flag it and you'll get a warning that, hey, the statistics are way off for this product.
I see. Okay. Okay, great. Well, thank you, Phil.
Yeah, my pleasure. Thank you. Thanks for the questions.
Sure.
Well,
very interesting. Yeah. Well, thanks for that.
Oh, thanks, Jochen. Good to see you always.
Have a nice day. I'm off now.
Give my best to some of the folks over there.
Okay, will do. Bye.
All right,
Same to you. Bye.
Okay, bye-bye. All right, well, I do try to keep these things to an hour, which I managed to stay pretty much on time. So, but if there's any other questions, please feel free.
Okay.
If not, you should get an email with a copy of the slides, some other technical data from the JP3 side. And like I say, feel free to reach out anytime.
Okay, appreciate Phil. Thank
All
you.
right, thank you.
Bye.
Bye now.